Hello, in this video I solved the third problem in the problem set 1. Let us read the question together. So let X be equal to the set containing of A and B, distinct elements A and B. Determine all metrics that one can define on this set X. Okay, so what a metric is? A metric is a function D which is defined with the domain actually X Cartesian product X to the set of real numbers. Of course, the output should be a non-negative real numbers by the first property that we demand on a metric. Okay, but what is X cross X? Let us try to understand this. X cross X means the set consisting of all ordered pairs whose components are coming from the set X. So there are only four possibilities that we can imagine. Either we have A and A, B and B, A and B, and finally B and A. Okay, so now I want to assign non-negative real numbers to these four ordered pairs. Okay, I want to discover all possibilities of assigning non-negative real numbers to these points, of course, in a unique way. Okay, so to do that, it's a good idea to draw, to have a picture here. So let me just write the points. So here, for example, the first point of this set that I have is A, and then the second point is B and B, and then the third point is A, B, and finally the last point is actually B and A here. And let me consider R non-negative. So let me use this symbol to denote the set of all non-negative real numbers. So I consider this to represent that set, and this is here 0. Okay, now I start assigning non-negative real numbers to these points. The first thing that becomes clear is that if I want to respect the definition of a metric, for this one I have to connect it only to 0. So I assign 0 to it because the distance from A to A itself should be 0 by the definition that we put for a metric, and the same is true for that one. So I have to assign 0 to that one as well. But what about A and B? One possibility is to see is that is it possible to assign AB to 0 as well. Of course, if I do that, to respect the symmetry, I have to also assign BA to 0. So this means that I am assigning every point to 0. Then, of course, I will construct a function. So that's the 0 function on the set X Cartesian X. So that is just saying that dx and y is equal to 0 for all choices of x and y in the set X. Okay, but is it a real metric? Yes, because the output is non-negative, it is symmetric, and it is very easy to see that it also satisfies the triangle inequalities. So yes, we constructed one metric. But so in this case, we also assigned AB to 0. But is it possible to assign AB to another point on this line? So let us explore that idea. So let us, for example, choose a non-negative real number. So let me call it R. So R is a non-negative real, a positive real number, not non-negative. I want to explore the possibility if this point can be positive. Okay, and let us ask myself, is it possible to construct a metric in which the point AB is assigned to R? If this is the case, then because I want to respect the symmetry property, I have to assign AB to R as well. So then what I have, if I call that metric, if I call that function d prime to differentiate it from what I have written before, so this d prime applies on A and A, applies on B and B, and it gives me 0. And this d prime applies on A and B, applies on B and A, and gives me R. in both cases. So, but the point is that, do you think this function d prime is also a metric on x? So to do that, we have to convince ourselves that this satisfies the properties of a metric. So the output is 0 or r, so the output is a non-negative number, 0 or positive r. And then d prime of x and y becomes equal to 0 if and only if the components are equal, because you see that if the components are not equal, I get a positive number. So the only possibility that I can have 0 is that the case that these two are the same. So it also satisfies the second property, and based on the construction that you see, it is also symmetric because there is no difference between d prime a and b by d prime and b and a by construction. So the only thing that you need to consider is the triangle inequality, but that's also a very easy task to convince yourself that this function also satisfies the triangle inequality. One way to do this is actually starting from scratch, consider all possible cases. But one idea that's also good is to remind you about the metric, actually, the discrete metric. So let me call it d to differentiate it from the other metrics that I have written here in this problem. So dx and y is defined to be 0 if x is equal to y, and it is defined to be 1 if x is not equal to y. And if you compare the metric d prime that I have defined here, you see that d prime is nothing except r times the discrete metric d. And we already know from the lesson that the discrete metric satisfies the triangle inequality. So if I multiply it by r, that's also satisfying that one. So that's also an indirect way of doing it. By the way, we can combine these two observations into one observation. You see that if I choose r, of course here I didn't allow r to be 0, but what happens if I still allow r to be 0? If r is equal to 0, so d prime becomes the 0 metric, which is also acceptable. So if I want to say what are all possible metrics that I have, I can define on the set X, I would say that every non-negative real multiple of the discrete metric is an answer. Okay? So all non-negative real multiples of the discrete metric are the only possible metrics that I can define on a set with cardinality 2. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.